So welcome. So this is Ampere's law, and the basic idea behind Ampere's law is that, as with all equations, we're looking for something that's conserved, and with something like light, we know that as we go further and further away from a source of light, the same number of photons is spreading out over a larger and larger surface area. So as we step further away, there are fewer photons per square meter, and so there's less light intensity, and that's why as you walk away from lights, they get less and less bright. Same amount of number of photons is leaving, but it's going through a larger and larger sphere. And so we can predict, actually, it's going to be an inverse square relationship in terms of the intensity of light versus the separation. Because of that geometry, it's got to spread out over a sphere, so it's an inverse square. And by the analogy, you can say, well, sound is going to do exactly the same thing, because that sound energy is going to go further and further from the sound source and spread out over a larger and larger area. And, you know, the area of a sphere goes as, 4 pi r squared. So it's an inverse square relationship. And same goes for, by the way, electrostatics, and the same goes for radiation. And, the thing about the physical sciences is once you know that mathematical way of describing that physicality for one system, you can recognize it in the others, which is quite efficient, actually. This is not spreading out. The magnetic field around a current carrying wire does not spread out spherically. If I was to guess, I would say it spreads out cylindrically. Points above each other, if I... Let's get my pen going. Yep. So a point here and a point here, same distance away from this infinitely long wire, just one's a bit higher than the other on my diagram, are identical. So there's no three-dimensionality to this, it's all two-dimensionality. And if I put a piece of card here and put my iron filings on it, I would find that the magnetic fields wrap around in a series of cylinders rather than a series of spherical shells. And so that gives me a different kind of symmetry. And so I can predict already that this will have a different kind of symmetry. It would be more like a cylindrical symmetry. So along comes Ampere, and Ampere is thinking about this kind of stuff, and he's looking for equivalencies, because that's what equations are. This is the same as that. And he starts thinking about how as you move further and further away from the wire, the magnetic field strength decreases. Okay, that's getting smaller. Is there anything that's getting bigger that can, kind of like cause constancy? And he started thinking about, well, maybe the length, the circumference of this loop. This happens to be a magnetic field loop. Maybe as I go further and further away, although the magnetic field strength is decreasing, this length of this circumference. So whereas with electrostatics we said when the electric field decreases, the area of the shell increases. In this case we're saying as the magnetic field decreases, the length of the loop increases. So do the two cancel each other out? And they do, in fact. So we say consider a magnetic field around a long, straight, current-carrying wire. As we move further away from the wire, the magnetic field strength B decreases, but the circumference of the circle increases. Is something conserved? And we say a line integral of B dot ds around any closed path equals a constant, mu naught times the current flowing through the wire, where I is the total continuous current passing through. And it's really any surface. So what I'm saying here is, if I have a wire and the current is coming towards me, I'm not going to draw the magnetic field. I'm going to pick a point of interest. There's my point of interest. I can play the same game I played with Gauss's law, where I imagine not a surface, but this is a loop. And I can turn around and say that for that loop, this imaginary loop, this equation holds true. Okay? So the integral of B dot ds is equal to mu naught times I. And that means that I can actually have any kind of shape of loop I want, like I had any kind of shape of Gaussian surface that I want, and that equation will still hold. Now, clearly, if I use symmetries, I can apply that equation much easier. So, question or comment?
Question. For, so, just so I understand this right, if we were to take, say, the total amount of, like, magnetic force, but if,
Force.
yeah, the total amount of, like, force, if you were to take around each other, that smallest ring around the wire, if you were to take the total magnetic force acting around that entire line, it would be the same as the largest line?
When you say total amount of magnetic force, force on what? Because magnetism isn't a force, it's a force on a charge.
Yeah,
moving charge at that.
Yeah, if you were to take the total amount, I don't know what energy, but...
Is it, so you're talking about of magnetic field? Is that what, is that the...
like if we were to take the total, I don't know what the amount of energy on that smallest ring, right?
Yeah, you see, and again, we're struggling for the words, aren't we?
Yeah.
Yeah. And I understand entirely, yeah.
I don't know, can I give it the same amount spread around?
Yes, the same amount of field.
Just spread out over...
So, it's the same amount of flux, really, isn't it?
Yeah, okay.
Because we can think of the arrow, well, yeah, it's the same amount of flux. And what happens is as we go further onto a bigger and bigger loop, the size of the effect gets smaller and smaller because it's a bigger loop. But yeah,
it is directly proportional. There's no...
it follows this equation. I mean, that's the so for a given current, as the total length gets longer, the B gets shorter. The good gets less. It literally follows that expression. And we'll practice it, yeah? Good. So can you see what happens there? It's like it's trying to describe something which is inherently quite sophisticated. And, he's looking for a word that expresses what he's imagining. And force is not quite the right word, and is it field, and all that kind of stuff. And that's part of the struggle. It's not just math. It's being able to verbalize and visualize what you're talking about. And what he was going through there is exactly what scientists have gone through from the very beginning. And you can look at notebooks from famous people like Newton. What always struck me when I looked at Newton's notebooks, you can see him hunting for the right word. And sometimes the right word's not been invented yet. And so he's going to put down 5 words because none of them are quite right. And so to that extent, as your strength and depth of knowledge improves, your vocabulary becomes clearer. And that's a lifelong thing. It's like, you get to the stage where... And that's why sometimes people seem really picky about a definition one time because they've kind of resolved things in their head. And sometimes people are vague, and you can feel it in your own physics. It's like, I'm vague on that bit, I'm sharp on that bit, because I've sorted this bit out. So struggle, keep on struggling with it, and it'll just get, And when there's not sure what word it is, it means dig a bit more. So well done, that's good. Okay, so what we're going to do is, and so this is an example where in these I started worrying about people, not taking notes and not listening. So I decided to try this thing where I put down the solution first, so I know it's right. I hope it's right anyway. And then you can watch and see where I'm going. So this is an example of a problem. So we says an infinitely long current carrying wire follows the y-axis. Using the method of Ampere's law as shown in class, show that B is equal to mu naught I over 2 pi r at a point that is r meters from the wire. So here's my point of interest, and this is r meters from the wire, so there's my r. I have my current flowing through the wire, and in this case, I am choosing to do a loop which is cylindrically symmetrical about the wire. There's nothing in Ampere's law that says I have to. Ampere's law is not saying the loop of the magnetic field. It says a loop. Because sometimes the magnetic field is pretty distorted. So it's important, as we just distinguished before, the Gauss's law, the Gauss's surface was designed by me. It's an abstraction, and I could pick a potato, or I could pick a sphere, or I could pick a cylinder, and some were better than others, making the math easier. So the same goes for this. So I want to emphasize, I'm not drawing this red loop because it is on a magnetic field. Well, it's not by law, it has to be on a magnetic field line. It's just in this example, I'm going to pick it, and it does coincide with a magnetic field line, and that's to my advantage. Okay? Because later on, we're going to do examples where we don't do this. So we say, well, okay, for this particular loop, which my point is part of, I can say that the line integral of B dot ds is equal to mu naught times I. That's just stating Gauss's, Ampere's law. And then B is, well, for my loop, because I have picked a loop which is superimposed on top of the magnetic field, I can say that for my loop, my B, which is circular, so let's do it. Yeah, my B, I'll draw my B here. My B is parallel to my little bit of ds. My little bit of ds is my little bit of length of my loop, and my B is at all points parallel to it because the two mirror each other. Well, that's kind of nice because my B is parallel to my ds, and when we know with a dot product that the magnitude is B times the ds times the cosine of the angle between them. And when the angle between them is 0, because they're parallel, I can forget about the angle. So I just made my math a whole lot simpler by picking that situation. And then the other thing that's kind of nice is I said, well, because I'm equidistant away at all points on my imaginary loop, that means that my B is constant for the loop. And so that can even come out of the integral. So there's two sort of cunning math steps I've taken because of the loop geometry that I picked. Just like in Gauss's law, we picked the geometry to suit the math. And so I can say, well, okay, if B is constant, then that can come out my integral. So B times the line integral of ds. Oh, the line integral of ds is just a circumference, and I know the equation for this. So it's going to be B times 2 pi r is equal to mu naught times I. Rearrange, and I got my answer. It's that. It's like that because I picked that loop geometry. If I'd chosen to do a square loop geometry, I could still solve it, but it would not be this simple. I'd have to do angles because my ds would not be parallel to B at every point. I'd have to take into account all those things. It's not that it's not doable, it's just it's not doable in 5 lines. So I'm being smart in the loop that I pick, you know, just like we did with good old Gauss's law. So using the method of Ampere's law as shown in class, determine the magnitude of the magnetic field at a point that is 7 meters from an infinitely long current carrying wire with 5 amps. Can you ever go at that? I'm going to put this on pause. I want you to just practice it now. There's no answers, so put it on stop. No, pause. So we just fly through this, and basically it's the same layout. In a test, I would be happy with you leaving the mu naught. I'd like you to work out the pi, just get into the habit of that. Mu naughts, I don't particularly want you to mess with, and epsilon naughts, I don't particularly want you to mess with, unless it's part of the derivation, you know. But pi's, we can work pi's out. Okay. Don't forget your units as well. That's a big common mistake on this kind of thing. So now, okay. In the intercession bit, we talked about how with Boyo-Savat, we had to have things in a semicircle to keep them, or a circle, or some element of a circle to keep the math kind of nice and comfortable. And Ampere's law, we don't, and so Ampere's law is kind of very, very useful. And this is another example of where we're using Ampere's law to solve a problem and develop an equation which might otherwise appear to be very hard. And so I want to, again, I'm using this idea where I write things down and then you guys can see it. So I have drawn a diagram of a solenoid, and I know that solenoids tend to be long and narrow and parallel so that the width is the same. And I would like to know, and the magnetic field is on the inside and very little on the outside, you know, negligible on the outside. It kind of comes out of the ends, you know, the magnetic field kind of comes out of the ends and goes in at the other end. And here there's not much magnetic field, so I can even say there's like next to no magnetic field by the side of a solenoid, just like there's next to no magnetic field by the side of a bar magnet. And so, okay, and it says, okay, you got this solenoid, show that this is the expression for the magnetic field inside the solenoid. N is the number of loops, number of turns in the solenoid. L is the length of the solenoid. I is the current flowing through the solenoid, and B is the magnetic field inside. And I don't use a circle in this case. I use a rectangle. But it's not just, you know, haphazardly. There's method to the madness. And I can divide this rectangle up into four different lengths. There's the top length, and there's the outside, and then there's the bottom length, and then there's the inside. I'm going to take these guys in turn. And the first thing I'm going to recall is that Ampere's law says for this loop and sections of this loop, if you like, the line integral b dot ds equals mu naught times I. Okay, so now let's look at that. For side 1, my ds is going in the positive x-axis on my diagram, but my b is going in the positive y-axis in my diagram, because that's the way that solenoids work. Bit of conceptual stuff there. I know that these are at 90 degrees to each other, and so I know for a dot product, when your two vectors are at 90 degrees to each other, you get 0. So I can say, yeah, this is great. Side 1, b dot ds equals 0. So forget about it. It's not going to contribute. For side 3, by the same argument, my ds is pointing in the other direction now, because it's follows a loop. So my ds is pointing in the negative x direction, and my b is still pointing in the positive y-axis, but they're still 90 degrees to each other. So again, b dot ds equals 0. So forget about that. For line 2, my ds is going downwards, negative y. My b is pointing in positive y direction. So they're parallel to each other. So I can't simply say that they're perpendicular, so forget about them. But what I'm using on this section out here is that the magnetic field is so small, it's negligible. So forget about it. So b dot ds equals 0 because b is 0 in this case, you know. And you can feel more or less comfortable with that. Is it absolutely 0? No, but it's like small. And that leaves this last bit, which is my only length of wire, which is this bit. And yeah, it's inside the solenoid, so B is significant. That's what I'm trying to find. And my ds is parallel to B, so this is where I do my Ampere's law math. So I say the line integral of B dot ds for side 4 is equal to mu naught times I. And B is constant. Okay, and B is parallel to ds, so I can say, okay, so I missed a step here. So because B is parallel to ds, B dot ds is equal to B times ds. It doesn't have to be a dot product because it's the magnitude of B times the magnitude of ds times the cosine of 0, which is 1. So then I can come down here and I can say, oh, well, in that case then B is constant. So in this integral, so this would be the integral of that would be the integral of that. It's a small point, but it's just, you know, detail. So then that means that I can take my B outside this integral, so I have that integral there. And then I say, oh, well, hold on. This bit here is just the length of this piece of wire. which is, oh. Well, I chose to draw a rectangle which wasn't the total length of the solenoid. Okay, it's a different length. It's shorter. We'll call it L dash. So my integral length is equal to L dash. And so my B times L dash is equal to mu naught times I. Okay. My current flows there, but it comes round again there, and 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 so on. So it's not simply I. It's going to be 1 times I, and 2 times I, and 3 times I, and 4 times I, and 5 times I, and however many times I have. Let's call the number of turns, or the number of loops inside my rectangle n with this little dash. So my expression now becomes B times L dash is equal to mu naught I times n dash. So then the next thing is, I'm not given n dash and L dash, so how can I find them out? And what I say is, by symmetry, the ratio of the true number of turns to the true length is going to be the same as the inside the loop number of turns divided by the inside the loop length, because it's a uniform coil. So n dash over L dash is the same as n over L, and so my equation becomes that. And I suppose the question is, why didn't I just make this loop the entire thing? And I don't have a good answer for that. It's like, maybe there's some subtle reason, but, it's the way it's traditionally done. So, sorry, comment or question?
It was good.
Okay. Okay, cool. So, I don't know what you feel about that. I mean, first glance, it's a complicated question. Where would you begin? But, by using Ampere's law wisely, it can fall out. Yeah, it's kind of nice. If this would come up on a test, I'd want you to express Ampere's law. I'd want these definitions, these justifications, and then I'd want you to get down to here. But notice what we did. We devised an expression that we used in lab for the magnetic field inside a solenoid, and we just pulled it out and said, here it is. But this is where it comes from. Let's have a look. How are we doing for time? We're doing all right. Let's stop this. So here's the layout. Pretty standard, where we did it before. The thing I noticed on this was when I put numbers in, the thing I can do is I can give you two lengths. I can give you the length which is the radius, which is 3 meters, which is irrelevant. And I give you the length which is the length of the solenoid, which is 6 meters, which is the required one, to see, do you know which length to use? Are you visualizing? Again, it's not the math, it's the visualization to inform the math that counts. So, just be able to go through that. If I say, using the method of calculus as shown in class, I want all of this. If I were to say, what is the magnetic field inside a solenoid, and you just know the equation, you can use the equation. It kind of makes sense if you look at the equation. It's basically saying the magnetic field depends on mu naught, pretty well they always do. The number of turns per unit length, that's, if you like, the density of turns. It seems if you have more density, you'd expect more magnetic field. Less density, less magnetic field. So that makes sense. Then the current flowing through it. I mean, it seems to me this is a pretty logical expression for this geometry. So there's not much memorization, I don't think. Yes?
Just for that diagram, those circles are cross-sections of the wire.
Those circles are cross-sections of the wire. It's like I'm cutting it, I'm looking at the cross-section of the wire. Yeah.
That wasn't clear to me the first time. I thought you were just doing like a very little loop, but it wasn't making sense.
Oh no, this is, no, I'm sorry about that, no. So this is the wire comes around and it goes through and I cut it and goes around. So the current keeps on being counted. Yep. Cool.
That makes a lot more sense.
Good, okay, So now we're going to invoke something we've seen before, which is flux, which is arrows. So, okay, we can imagine, I've drawn a solenoid down here and have the arrows, and the difference between this and, positive charge and negative charge is that the arrows truly started on the positive charge and they ended on the negative for electrostatics. Whereas in this case, they actually don't start and end. They continuously form loops. And so it kind of makes the equivalent of Gauss's law, the magnetic equivalent of Gauss's law, a bit less interesting. Because no matter when things come in loops, no matter what Gaussian surface I draw, my net flux is zero. Yeah? The reason why I get a net flux on an electrostatic is because I can put the charge inside the actual loop, the Gaussian surface. I'm sorry, I'm saying loop, I mean the Gaussian surface. I could choose to put my Gaussian surface outside and the net flux would be zero. Here the net flux would be positive, here the net flux would be negative, okay? But on a diagram of magnetic field lines, no matter which surface I choose, the arrows never end, so by definition, every one that comes in leaves. I can't draw one where it enters and does not leave, or leaves and does not enter. So my integral of B dot dA is just zero. It equals, my integral of B dot dA over a surface is equal to zero. So I can define flux. Yeah, flux is the number of arrows. And I can say it's equal to the integral of B dot dA. But the answer is, well, yeah, and that always equals zero for this system. So it's less interesting. It's true, but less interesting. So we say, consider an area section of a surface. We define an area vector just like before. And we say, okay, there's a magnetic field permeating this region. What's the flux? Well, the flux would be equal to the integral of B dot dA. Unit of magnetic flux is the Tesla meter squared. That makes sense. B times area, which is sometimes known as the Weber or Weber. Because the magnetic field lines are closed loops, then hey, guess what? The answer is the flux is always zero. So
magnetic flux is just always zero.
The magnetic flux is going to be zero. Yeah.
So why do they bother to give it to units if it's always going to be zero?
Two reasons. One is that it's an analogy to electrostatics, right. And second is sometimes that's informative. I can't give you a detailed example, but it's important to know that it's not zero. Pardon? So the reason why I'm hesitating is because I know that we do measure some things in Webers, so it's like I think so. I got to be careful here. No, I misspoke. The flux through a closed surface is zero, but the flux need not be zero. If I choose not to do a closed surface, if I choose to do a open surface like that, that magnetic flux is not zero.
Okay, I understand.
So Gauss's law, the equivalent to Gauss's law, hey, the answer is zero. But flux itself is not zero. I'm sorry, yeah. Glad you caught me on that. The net flux through a closed surface is zero. Yeah, cool. Okay, so if we look back at our electric field versus our magnetic field, then what we see is that for Gauss's law, the integral of E dot dA is equal to the Q in over epsilon naught, which was really useful. And the equivalent, the magnetic flux, which is equal to the integral of B dot dA, is equal to zero. So there is an issue with Ampere's law and capacitors, and that is this. All right, so if I define a loop, this is my imaginary loop. And here's my capacitor. I'm showing it really spread out. So here's one plate of the capacitor, and here's another plate of the capacitor. And if I choose to just have the current inside the loop, the current passing through the loop, as being the current that goes through like the tambourine skin. Imagine there's a skin there, and you say what current's passing through it. Then there's, at different times there's current flowing through that wire. But there was nothing that said that that has to be a taut membrane. So I could define a skin, if you like, as going in the gap, in which case there's no current flowing through that bit. So I get two seemingly inconsistent answers, based on how I look at it. Remember, Ampere's law says that, and consider path P. So path P is that guy round there. S1 has current flowing through it. This is this surface. S2 does not have current flowing through it because I warped it. How can we resolve this conflict? And what they do is they say, let's pretend there's a current flowing through the capacitor, and we call this our displacement current. And so we need to define the displacement current, and my displacement current is equal to epsilon naught d phi E by dt. And frankly, for our class, just know that this exists and know it develops this equation. But I don't expect you to know this equation, and I would not expect you to use this equation. We just say, well, okay, so we get what we call the Ampere-Maxwell law, which is that the integral B dot ds is equal to mu naught I plus my displacement current. I added this displacement current in. So the integral of B dot ds is equal to mu naught I plus, and the displacement current is mu naught epsilon naught dE by dt. Okay. Yes?
Why doesn't the one surface have any current flowing through?
Because current can't flow through the gap of a capacitor when you think about it. The field can. The reason why the two plates are connected is due to an electric field, not because current flows. Okay, now we talk about current flowing on the circuit, but it's like, if you have a parking lot on the south side of the Sunshine Skyway, you have a parking lot on the north side of the Sunshine Skyway. I can drive out of one parking lot and go to the northern one over the bridge. I can go from the northern one to the southern one over the bridge, but none ever went across the water. So in pure terms, no cars passed the water, but in practical terms, they got from one parking lot to the other. And so it's a bit like that with this. So there really is no current flowing through the gap, but it acts as if there is. So that would be like, who cares? Who cares? Well, what it turns out is this becomes quite an important equation. So we end up with this Ampere's Maxwell law, which again, I only want you to know about. I don't want you to remember, and I'm not going to ask you about it. I'm just giving you some. If you're going to be an electrical engineer or a physicist or whatever, this is going to come up again. Because later on, when we talk about Maxwell's equations, we're going to talk about Gauss's law, and we're going to talk about, there's four of them. And basically, this is going to be one of them, or the basis of one of them anyway. Okay? So it's just a little bit of preempting. I've noticed in the new edition, this is actually moved back to where we talk about Ampere's law, so fair enough. So on this last bit, just know it's there, and that's all you really need to know. Okay? Cool. I'm going to stop there.